All right, welcome everyone to the Global Water Futures Core Modeling and Forecasting Team's Topical Webinar Series. My name is Praveen Rokaya. I'm the Science Coordinator of the Core Modeling and Forecasting Team. It is my pleasure to present you today a webinar on advances in large domain hydrometeorological modeling. Today we have Dr. Andy Wood from the National Center for Atmospheric Research in Boulder, Colorado. Dr. Wood is a leading expert in the areas of streamflow forecasting, hydrologic modeling, climate change downscaling and impact assessment, and water resources management. He was previously a visiting fellow at the Institute for Water Resources of the U.S. Army Corps of Engineers, a research assistant professor at the University of Washington, the lead scientist of private firm Three Tire Inc., and a development and operational hydrologist with U.S. National Weather Service River Forecast Centers. Dr. Wood has also long been active in service activities in the field of hydrometeorology. He chaired the Hydrology Committee of the American Meteorology Society and was an editor of the Journal of Hydrometeorology. He also co-chaired HEPEX, served on the advisory board for the ECMWF European and Global Flood Awareness System, and now sits on a WMO standing committee for our system modeling and prediction. Dr. Wood's current work centers on pragmatic application of our system science to improve our understanding and management of water, energy, and terrestrial ecosystem, which I believe he will be highlighting today. Without taking much time, I want to kick off this webinar by thanking Dr. Wood for graciously accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Wood, the floor is yours.
Thank you, Praveen, and thanks to Martin and to the Global Water Futures group for inviting me. I'm really happy to be able to present some of the work that we've been doing lately, and it's really a culmination of work that began when Martin Clark was still with us at NCAR and has continued to some extent since through collaboration. I was lucky enough to visit him up at his lab right before the pandemic hit to just kind of reinforce that relationship. In any case, this is really about trying to bring forward a new set of data sets and modeling tools motivated by answering some applications needs in the water management community. So let's see. I will try to continue here. Sorry about that, had a lag. In any case, one of the early motivations came back right before I came to NCAR in 2013. I had participated in helping to write a report with the major water agencies in the US, the US Army Corps of Engineers and the Bureau of Reclamation. I was working at NOAA at the time, but trying to identify user needs in water management. And there were a number of categories in the report, but one of the things that was highlighted through polling of all the different field offices in the Corps and the Reclamation across the US and Western US was that there's still a lot of strong desire for improved forecasting, whether it's precipitation or short-term stream flow or longer-term seasonal stream flow, and more information to help quantify uncertainties and quantify the quality of the forecast. So with this kind of motivation in mind, we strategized about kind of the major areas in which we could try to improve the capabilities for water management. And they included, as we'll get into, things like better meteorological forcings, better modeling, better methods for using weather and climate forecasts, and connecting them to applications. And to some extent, I think if we look back at the history of forecasting, at least in the US, by the operational agencies, the water managers may have somewhat of a point. Like this is showing about a nearly, 15-year sequence of skill assessment of forecasts at one river forecast center in the Southwest. And if the blue line is just using a persistence forecast for stream flow one day ahead. And then these red and green lines are showing trying to improve upon persistence with using models and weather forecasts. It's not entirely clear that the gap between the two lines, using the most basic forecast possible, which is the blue, and using models and weather forecasts has really improved that much over that period of time. And so it brings the question of how we can bring new techniques and models and data toward this challenge of making hydrologic information available for applications such as forecasting. So what started to happen in the last 5 to 10 years is that there's more of a convergence in different communities who work on the land surface or work on hydrology. On the one hand, far over on the right, you have the operational streamflow forecasting and hydrology community running real-time models, making predictions. That's been doing this for decades, and for the most part, kind of using simpler conceptual, less process-oriented models, but very complex workflows. Now, on the other hand, you have different, more researchy communities shown in blue, such as this high-resolution watershed process modeling community, the land modeling community, or land surface modeling community, running models over large domains. And then even beyond that, the coupled land modeling and Earth system model contexts are within numerical weather prediction systems. And so now there seems to be more of a attempt by these groups to, particularly the research groups on the left, to use their models in an operational context or to provide usable, actionable information, whether it's operational forecasting or even, climate change assessment, impact assessment. And there's some notable examples of this, such as the National Water Model in the US, the NWM, which was high-resolution gridded watershed model applied over all of CONUS in the US for forecasting. It's been for a long time the NLDAS effort, which is sort of intermediate scale, which has turned up, and that's a set of land models run in real time over the country. And probably the most high-profile application is drought monitoring. And then more recently, there are global examples like the ECMWF numerical weather prediction system, from which you're taking gridded runoff and routing it to provide stream flow as kind of a byproduct of the NWP process. So in general, what we're seeing is these more complex process-oriented models being applied in places where we used to have this conceptual watershed aligned modeling. And I would make the point that, we have the computing power now to generate street scale outputs. And this is just an example showing in the Boulder, Colorado area output from the National Water Model with these very finely resolved parts of the stream channel network, each having values for flow being simulated by the model. But that doesn't always mean that these outputs that we can generate are usable or good enough quality to support decisions, in part because there's a lot of science that needs to be still resolved to support, some of the challenges of modeling at this scale. So one of the major motivations for me and for others I've worked with, such as Martin Clark or Bart Nyssen at the University of Washington, is the idea that we like to kind of inch toward this ideal of using these heavy, complex process models from the starting point of operational hydrology using more simple lumped conceptual models with some sort of intermediate that gives us some of the process resolution, but without pushing us to the point where we can't calibrate models or get usable results from them. And just before I go further, I also want to make the point that operational hydrology is not just about models. Oftentimes the discussion of operational hydrology can focus on which model a group is using, and the major advance is seen as a new model. But it's there are a lot of parts that wrap around operational hydrology models. If the blue is sort of the modeling core, you obviously have to have high quality meteorological inputs, whether observations or forecasts, You need methods such as downscaling of these meteorological observations or data assimilation to kind of bring the model back on track when the real-time forcings throw it off track. You need powerful methods of parameter estimation, and then more recently, methods of post-processing outputs from the model. So there are a lot of techniques that get wrapped around it. I'm going to start off by talking a little bit, before I get to the models, about some of the work we've done to improve the meteorological inputs to the models. One of the major tools that we've developed, and this is from work and methods developed by Martin Clark back in the 2000s with Clark and Drew Slater's paper on snow modeling, is this idea of using spatial terrain enhanced regressions to predict local meteorological quantities. And then by dint of using locally weighted regression in the area of a given observation point that you're trying to generate, you also have a way of generating uncertainty from the prediction model or the spatial regression model. So in this technique, it has two steps. One, there's a use of this spatial regression over station observations in the neighborhood of a grid cell, where you're trying to predict the distribution of meteorology and the station observations from the terrain features surrounding it on a daily varying basis and spatially varying basis. You can predict the probability of precipitation, and then from that, you can move forward to a step of predicting the amount of precipitation and other quantities like temperature. And this is just for an example of a test domain early on in the Colorado headwaters, in which you develop this statistical regression model to make these predictions. And then you can sample from spatially correlated random number fields to sample the statistical model to create different realizations that are consistent with the station observations, and then use those random numbers and sampling to generate different forcing amounts, such as precipitation. So for example, there are three ensemble members shown on the right with the random number, spatially correlated random number samples leading to different realizations of precipitation, all of which are equally likely given the observations used to train the model. So that's kind of a mouthful. Kind of what it looks like is that you can get out, large scale. It's fairly efficient code. It's called GMET. It's available on GitHub. But you can get out these sort of large domain analyses of precipitation and temperature, and this is showing precipitation on the left, temperature on the right in the United States, as well as the uncertainty. So we have the ensemble means on the top and the ensemble standard deviations on the bottom. And from that uncertainty, we generate these ensemble members of forcings, so that now when we drive a hydrology model, we don't have a deterministic estimate of the hydrologic states and outputs such as stream flow, but we actually have an ensemble that's driven by the uncertainty in the meteorological forcings. So we felt that this was a really important tool for developing these improved operational hydrology applications. And we've used it in things like model calibration, data assimilation, and then even other validating other models. This is just another example of what these ensemble members look like for one of the applications I've been working on most in the last couple of years, which is the Western US. And you can see, a whole number of equally likely realizations of precipitation during a one-day event in 2019. And then the temperatures kind of gives the impression that just from the observation-driven meteorology, there is a lot of uncertainty, and that can be useful in these applications. One final comment about this precipitation forcing data set is that in comparison, and this would be the Newman et al. Depiction here, since the Andy Newman's paper kind of updated the spatial regression approach and introduced GMET. If you look at the applications like trend assessment and long-term trends in climate, it does actually appear to be a very well-behaved data set in comparison to some of the other very common meteorological forcing data sets such as CML-DAS or DayMat is another one, or LIVNA, which is kind of akin to an early Maurer et al. Long-term data set, where the spatial regression characteristics lead to smoother trend fields that are more akin to PRISM, for those who know that data set, than some of these other data sets. So we're pretty happy with the way this works, and it seems to have been also validated by being able to produce good quality hydrologic modeling results. So moving on to the hydrology models, there are a number of ways to do forecast applications, and that's always pretty high on my mind as I think about a model implementation. You know, there's kind of the traditional in-the-loop forecast paradigm with these conceptual low-dimensional models that can be tweaked by forecasters who are quote-unquote in the loop by being able to manipulate model states and outputs, versus the newer kind of over-the-loop approaches where you run a model in a more automated fashion that allows you to go to higher resolutions and more complex models. And there's some major paradigms in that area where some people are running these super high resolution, but deterministic because they don't have the computing power for ensembles types of approaches. And other people are doing this coupled approach where they try to take runoff out of coupled NWP systems or climate systems and use that instead of a standalone hydrology model. And I've tended to opt for the medium resolution or intermediate resolution, intermediate process complexity, ensemble suitable modeling approaches. And for this, we've been using the ZUMA model, and we've had a number of different applications. And I've also started to move away from the gridded modeling approach toward a watershed aligned modeling approach that's a little bit more akin to what was done traditionally in operational hydrology with these watershed models, versus all this newer these gridded approaches that have tended to crop up in the other research paradigms. And so we had a number of studies over the last 4 or 5 years to push this forward. For those who haven't seen ZUMA in one of the earlier seminars in this series, it's a process-oriented framework, more so than one model, where it tends to offer, well, it offers different options for parameterizing key fluxes in the land surface to update, you know, the major states that we all agree on that are present in hydrology, and it very nicely separates out the numerical solution of this system of equations, which is not always the case in hydrology models. So, you know, there are a lot of reasons to like this model, which is why I've invested a lot of my project effort into trying to move it forward into applications. Just an example of the kind of process or parameterization choices that a consumer user would see is shown here, where there's kind of a model decisions file. And again, I should say this is all kind of created by Martin Clark, who you luckily have living with you north of the border lately. So kind of a lost resource for us, but we can still use some of this productivity in the modeling arena. Anyway, Martin has created this framework for being able to select different parameterization decisions, and then beyond choosing, say, different methods for specifying the Richards equation or stability function for above the canopy or infiltration techniques or hydrologic conductivity profiles, one can also organize it in different ways with different kinds of connectivity, both in the subsurface and across grouped landscape units. And I think this hierarchy between group response units for hydrology and hydrologic response units that are nested inside of them is going to be a really powerful capability for our ability to implement this model in a process-aware way. So some of the first steps in this modeling were to stand up a model that actually had a usable a priori configuration that could give, excuse me, that could give credible outputs for all the major fluxes, both water and energy balance, over a large domain. Initially, the model framework was just code, and now we have built it out so that it has this a priori set of parameters and can now run a little bit more off the shelf. So in this particular development work, we started with gridded and LDAS domain, which is what's shown here, forcings, meteorological forcings, and then use the 1/8 degree resolution. I decided to use 3 soil layers. That's a similar choice in a lot of other land models, with a limit of 5 snow layers. And we activated an aquifer layer, which provides for more control over base flow. We set it up with 1 hour and 3 hourly forcings from an LDAS initially, and then later from GMAT. And then I went through and exposed about 40 parameters that could be used for calibration associated with some of the major processes one would want to calibrate. And this is just an example of kind of what some of those processes are and what they relate to, or some of those parameters are and what they relate to. And those are available now in a trial parameter file so that one can work this model into a calibration or optimization routine. And some of these are distributable. Here's a number of distributed attributes and parameters and what they look like in this initial a priori implementation. The other part of the modeling is to use a routing technique. And Martin and his colleague Naoki, who works at NCAR, Naoki Mizukami, has spent the last few years building out a multi-method, efficient routing tool called Mizaroute, and we've implemented that, or I should say Naoki and Martin, on several different stream segment networks, such as NHT Plus, or the Merit network, which is quite a bit coarser, and added some other kinds of attributes that are helpful in parallelization, nesting, and subsetting the model. And as part of this development work, some of it was funded by a NASA project that Martin originally started. And within the context of that project, we were able to run the a priori model in a climate change context. So running it out for 100 years into the future with multiple meteorological forcing data sets derived from different GCM scenario simulations of climate in the future. And this is just showing an example of runoff in different seasons from the ZUMA model, a priori model, between 2 different future climate scenarios. So the point is really to show that it has this climate change context capability now. And here's an example of what the stream flow with the Merit routing network look like associated with those future climate runs. And this is for the year 2051. You know, when I step back and think about the ability to do this kind of work after starting, you know, back in 2013, 2015, without any of this really fully existing or runnable, I think it's pretty remarkable. And it really makes for a new and I think powerful set of at least modeling tools that we can bring not only to climate change, but as I'll show also to forecasting. So although I've done a lot of work in climate change, and part of my interests are always down at the watershed scale and the forecasting and water management. And so from this gridded baseline model, we basically started to develop tools and workflows and techniques and refinements and bug fixes and things like that that could have let us start to simulate on this watershed scale. And this is showing going from this 8th degree gridded model to kind of an intermediate scale watershed version of ZUMA. We were able to remap a lot of the parameters and attributes and forcings into this watershed basis for a bunch of different basins. As part of this, though, in this idea that we need to go from a priori model to a model that had real parameters and calibrated parameters and could give good quality results suitable for use in forecasting water management, we also set up CAMELS, large basin sample of watersheds from ZUMA. And this is work that Martin was also heavily involved in triggering when he was back at NCAR, basically supervising Andy Newman and Nan Zador and setting up these CAMELS attribute data sets and initial model enforcing data sets. So we basically emulated that with ZUMA. And this is actually an extremely useful data set. I didn't quite appreciate when I first started using it, but the ability to look across and efficiently simulate a wide variety of catchments and then look for consistent tendencies or deficiencies and work on small subsets of that data set to try to resolve problems in the simulation has all been very powerful, in figuring out, like for instance, that snowmelt dominated basins have a certain tendency of errors that we could then go hone in on and focus on the processes leading to the errors was really useful. And then this CAMELS data set was also used in Martin's course at University of Saskatchewan, and it's being used in the SFA HydroShare for educational purposes. Here's just an example of some of the water balance variables in one of the locations where ZUMA does quite well out of the box. Down on the left, it's a total runoff versus stream flow in this little basin, and it's quite a remarkable simulation to get with no calibration at all. And so from this, I was able to go in and find an efficient set of optimization parameters relating to different processes for transmission of moisture through the soil, storage of moisture, infiltration, evaporation controlling parameters, and then some sort of bulk parameters related to canopy that control snow accumulation and melt, and then link it in with some new workflows to some optimization software. And these are now also being used much more widely with ZUMA, such as within the University of Washington group and up at in the Canmore group. So we at least have the basic workflows to be able to do model applications with this. Alongside of all that model and workflow development, we also have an NCAR system for, like called SHARP, system for hydromet analysis, research and prediction, that has a lot of workflows for bringing forecast data in to format into inputs for models such as ZUMA and drive the models in real time, and also for hindcasting to be able to go back and explore the quality of streamflow forecasts over a long period of historical forecasts. And so this tool, and it's really more of a collection of methods wrapped around real-time scheduling workflow, has been a big help in setting up some of the forecasting applications I'm going to talk about next. So drilling down with this watershed model, we've had a number of projects, probably a half dozen, to start to look at how you could improve forecasting in very specific operational settings. And this is just one project with some colleagues, Dan Brown and Jordan Lanini, and the CU Center for Advanced Design over in which they work on reservoir models. And for this project, we've been developing seasonal forecasts and hindcasts with ZUMA to run in for the Buffalo Bill reservoir inflows. And so this shows the discretization of the ZUMA model along these watersheds, which are USGS HUC 12 boundaries. This particular reservoir system has two forks. It's on the Shoshone River, and this is just showing what it looks like in a real map with a little town down below. It's fairly near to Colorado, and so we've been able to use these workflows and model implementations to get good quality, I would say not perfect, but certainly decent quality long-term simulations from ZUMA that we can then use to run these hindcasts. So here's, for example, a set of 50 years of, or 49 years of 49 member ensemble 1 year hindcast predictions of inflow for this reservoir that can be used to train a new reservoir operations model that is trying to understand how much information can be gained from forecasts to improve the water management. And there are a number of others of these kinds of applications too. In the Rio Grande River Basin, which is south of us, there's the headwaters of the Rio Grande is a runoff producing area that sends water down into New Mexico and into Texas and eventually through a treaty to Mexico. So we've set up the same model, the watershed-based model, to forecast inflows at around 20 points that are used by an water operations model. And we've been able to give these hindcasts to reclamation and then explore their skill, and then also to some extent how they could be used to help form annual operating plans. We have, I'll mention a few other studies in the slides to come, but we also use ZUMA in a real-time 1 year long flood forecasting competition that went out 2 days called the Shootout. We have a new study forecasting for reservoir up, also run by reclamation up in the Big Thompson River, which is near us. So now that we have these baseline ZUMA configurations built out, and particularly all the scripts and the ecosystem of tools around it to be able to implement it quickly and analyze it and share results with stakeholders, we're able to kind of undertake a lot of these kinds of new applications. And it's, I gotta say, it's very gratifying to get to this point. Here's another example in the Rio Grande River Basin where the question was whether or not you could take the hydrograph shape from a ESP Ensemble Forecast and use that as a deterministic input for the operations model, because this is the workflow that's used within the water management agency to develop the annual operating plan each year. So we were able to use the ZUMA-based forecasts that we'd set up and calibrated. And this was a lot of heavy lifting by a staff member named Josh Sturdivant, who recently left NCAR, together with our colleagues from Reclamation. But we were able to at least demonstrate that some of these ESP techniques could give these credible hydrograph shapes. And here's looking back at April 2019 in one of the locations in the NCAR-based, ZUMA-based forecaster in red, and then the analog type technique that was being used in reclamation is shown in blue. So, you know, the point is not to necessarily be a bake-off and show that you can do a better forecast than someone else, but more to explore what possibilities are enabled by having this hindcast and ensemble forecast. Another aspect of this work is building out interfaces that we can use to share results with some of our stakeholders. So working with someone else at NCAR, staffer named Andy Gatos, who's more of a software engineer, we're able to make use of some tools at NCAR and develop kind of these data display, web-based data display capabilities for the ZUMA modeling. And this is just showing one example with where you can go in and sort of click on a location and pull up the, you know, stream flow information, the observed stream flow information, and the simulated and different state information to be able to kind of query the model and understand how it's performing. So this capability has been implemented for this West-wide model simulation and also for some smaller subsets of it. Here's another example showing the West-wide implementation of this, what's called the Hyperinspector. And this is another, on the right, out of the box, ZUMA Miserat simulation. This is in the Tuolumne River, where right out of the box, the quality is not too bad. Now, that's not actually true everywhere. There, no one would be surprised, but there are many places I would never show, never click on if I could help it, where the performance will need a lot more calibration. But even to be kind of on the same page with an a priori model implementation and forcing data set, I think is fairly encouraging. Here's another example. This is showing, I think, the North Fork American in California with a little bit of a zoomed in view to show how this intermediate scale modeling implementation looks on a regional level. So that's another component of the work. And I'll just talk about a few more final projects before I stop. One is validating ZUMA against some high resolution snow data from the Airborne Snow Observatory. This ASO SWE data has been touted very strongly by the proponents recently for being able to offer completely unbiased estimates of snow accumulation in the mountains that can then be used to predict runoff with very, very high accuracy. And so we have a study to kind of evaluate some of these claims and see the extent to which the very much higher resolution snow data that's collected in the mountains actually does support marginal improvements in water supply forecasting. And as part of this, we're also using ZUMA for water supply forecasting in this Tuolumne Basin, which is shown on the right. And here's just an example of comparing kind of at the HUC level, the ASO SWE patterns versus the ZUMA SWE patterns. And, you know, despite some disagreements, they're actually, the overall pattern is actually quite good from ZUMA. And then here's some, with that same kind of HUC level model, I think it has 13 different spatially lumped HUCs. I'm showing the agreement between the ZUMA model, which has been calibrated for stream flow, not snow, and some of the snow measurements from the ASO satellite or airborne imagery. And although there are some years where there are disagreements and some may even look a little bit systematic, like kind of a under simulation in low snow years from ZUMA. In other years, there's really quite good agreement. So sort of suggesting that even if you're not calibrating directly for snow, by calibrating for runoff, you can actually, in this particular basin, you can actually dial in some of the performance related to snow as well. On the bottom, these are predictions of spring runoff from the time of the forecast to the end of July. And so the amount of runoff goes down as you get closer to the end of the period. But again, the ZUMA model trained on stream flow is doing quite well in making this kind of prediction. So to date, like this first phase or level of model implementation is focused on this intermediate scale with these hydrologic units. HUCs are about 90 square kilometers with spatially lumped characteristics, but still underlying process physics. And so now the question is, and this is motivated by interactions with water management, do we need to go further in the way we resolve the landscape to be able to resolve the snow and runoff variability and heterogeneity that leads to phenomena like spring flooding? And one of the contentions is that with the spatially lumped models, you may not resolve important, low elevation versus high elevation timing and snow response, which is true. And then the question is, how much does it matter? So with Hongli Liu, who was with me for the last year and a half or a little bit more before joining Martin in Saskatchewan, and then with Dan Broman and other colleagues at Reclamation, we've been working toward this next level of ZUMA implementation where we develop the ability to discretize these basins based on known factors controlling runoff. So for example, elevation is a known factor, due to high and low elevations. We always see as we go around, mountainous areas that you have snow at the tops of the mountains and less at the bottoms of the mountains. So one of the logical first steps is to discretize the basins based on high elevation and low elevation. And then we have a number of other levels where we take into account canopy versus non-canopy, because that's also a major control on snow accumulation and melt, and aspect, which in our terms we're specifying by radiation loading, so that we don't deal with saying specifically what angle the aspect is, but more calculating the relative strength of the radiation loading on a slope. And so those subsequent kind of discretization factors lead to more sub-GRU breakdowns in hydrologic response unit. For example, on the left, we have the elevation combined with canopy versus no canopy. And you can kind of see the, low elevation areas in blue split into tree covered and non-tree covered. And then finally, the one that we're looking at before we finish this research or this particular experiment will be also this radiation loading. And on the right, we see what the discretization looks like if you include, north facing or south facing or relative impacts of slopes on the radiation input. And we haven't completed simulations for these yet, but we expect that we will see a better ability to discretize some of the, or to resolve some of the variability in stream flow. And about where I wanted to stop. So this is the final project that I'll mention, and there are a few others, but in this particular case, we're taking this watershed ZUMA model with the MISA route implemented on Merit and using it to really tune up and calibrate a Pacific Northwest Columbia River Basin model that will run at this 3-hourly time step. The first project in setting it up has been to work on basins that are needed for climate change impact assessment. And this is a project led by Ethan Gutman that I'm involved in with others, Naoki and Bart Nyson and Chris Florence from the Corps, Jeff Arnold from the Corps. And so this is showing some of the progress as we start to calibrate all the headwater basins, and our calibration is reasonably effective on an independent basin level. You can see the blue uncalibrated bar of performance going higher most of the time in the validation once it's been calibrated. We do need to work on more of a regional model calibration strategy, but in any case, this will set up modeling that I will then use in Ensemble Springfield forecasting for a project that will start later this summer. So with that, I'll just summarize. This is work that NCAR and partners have done over the last 4 or 5 years to go from having this initial ZUMA model code and build it out into models that can be sort of a family of model implementations that can be easily adapted to applications, and then writing and developing all the workflows to share with other research groups to be able to set up the model and use the model and run the model, evaluate it, put it into forecast operations and things like that. And so we have a lot of new capabilities that we're pretty excited about now that the ZUMA model has become a model that will take us beyond where some of our legacy models took us before, like the VIC model or the National Weather Service models or the National Water model. There are some huge challenges in front of us. We still need to understand how to move forward with this model complexity and discretization appropriately in different applications. We need to understand how better to do regional and targeted scale parameter calibration, and continue to build out this ecosystem of workflows and tools. And then finally, just expand the range of applications that we're using for whether forecasting or climate sensitivity analysis. I'd like to use it in the Colorado Basin, given the impacts of climate in the southwestern US, and then just keep building out our collaborations. My hope is collaboration between NCAR and Saskatchewan will continue and expand to other groups in Canada. And so with that, I'll stop and thank everyone for their attention and invite questions.
Thank you, Andy. That was brilliant. We'll be now moving to question and answer session. Let's see if there is a question from Mazda. Thanks for your very informative presentation. I was wondering, based on your study, do you have any suggested classification for HRU or GRU for US or Canada?
Can you ask that again? Do I have any what?
Suggestion for classification of HRU or GRU for US or Canada?
We really, so I guess one thing to comment on is that I don't think there's any optimal necessarily way to define watersheds. You know, the scale can vary between, depending what you want to do with the model. Within the intermediate scale GRUs, I've used kind of a blend of Huck 12s, which is a data set from USGS, and then the Merritt basins, which is another hydrography data set that's already being used by Martin and others up in Canada. And I don't think there's much difference between those. Where, you know, selecting the HRUs, that is really going to be very application dependent. As soon as you break down in those discretizations to higher levels of complexity, you know, here we go from 18 GRUs to resolve this basin to 120 computational units. So that's kind of a scaling up by a factor of 6. That may be worth it for some applications because you really need it. In others, you may not want to incur that 6 times multiplier in your computational demand for running the model. Right now, we can run the model splitting all these HRUs apart in little groups or individually so they can run in parallel. We don't yet really have the ability to do that with the HRUs because they need to come back together during the simulation to exchange fluxes or be average. So there definitely are some things to work out on what the best strategy is for doing these definitions and figuring out how much resolution on these processes are major factors you need for a given application. You know, on the long-term climate application for larger basins, you may well capture enough variability at the GRU scale that you don't need to do much with the HRUs.
Thanks. I'm wondering for climate change assessment studies, so one of the critiques sometimes I get is that when we have to transfer the parameters that you calibrate for historical conditions to future climate, sometimes you know, there's some comments like you cannot use the parameters that were calibrated for one set of climatic conditions in historical period and use that for the future period. So I'm just wondering, what is your approach on dealing with those transferability of you know, calibrated parameter sets for the future climate conditions?
Yeah, there are two transferability questions. One is transferring in space because you can't really calibrate everywhere, and so you have to estimate parameters in some ways for places where you don't really have observations. And that's going to be a long-standing challenge. It was assessed during the Prediction in Unengaged Basins initiative over a decade, and you know, some progress was made, but obviously the better we can do to have confidence that even when we transfer in space, we can believe that our model simulations are realistic. That's going to help us. In terms of time, I often think that people kind of underestimate the ability of a model to simulate in different climates when trained in our past climates. You know, if you look at any time series, you know, in many locations over, say, 20, 30 years, you will have a large range of variability in the meteorological conditions that drive the model. You know, going from years where you have very low precip and high temperatures to years where you have a lot of precip and cold temperatures, build up a lot of snowpack, just to use this example to illustrate it. So to the extent that your model can handle that variability that's in the historical conditions, you do have some ability to handle change, you know, where instead of one time out of 10 years, you get these low years, a low year like this, maybe now you have, you know, due to temperatures and precipitation changes, maybe that's half of the years in your sample. And that does have secondary effects on things like long-term groundwater and water table and surface water, groundwater interactions, things like that, and vegetation, how it grows and changes. So, but I do think that if you have a model that can represent historical variability, that to some extent gives you a model that can look ahead, as long as that variability has not changed so dramatically that you're really talking about a different watershed. And then in that case, maybe you can start to do things like looking at analogous watersheds that are already in your sample to see if your basin has become one of those other watersheds, in vegetation and in climate. So I could go on a long time about that, but there's not really time.
Thanks. Okay, I think there's a question from Martin. Given the emergence of the mega drought, can you comment on some of the challenges and opportunities in predicting drought?
Yeah, I mean, I think this is one potential weakness of some of these model implementations, in that in basins that are affected by long-term drought, so 20-year low runoff, low precip, maybe higher temperature conditions, you may have some connections in the subsurface that are being altered, a loss of connection between surface water, groundwater, deep groundwater, and aquifers. And these models, that we're running, like the ones I showed today, don't really have that deeper subsurface interaction. And so I do think there'll be more development needed to try to quantify that. I think the community for a long time has suspected that these models that resolve the top 2-3 meters of the soil cannot really resolve or simulate the kind of hangover that you might get from one year to the next from being in a drought and moving into the next year because of this sort of truncated subsurface. But I think we can work on that and expand that subsurface to try to see if that helps us simulate these effects. I would say that one other thing that we need to do in the way we calibrate these models is to take into account some of the characteristics or features of the model that influence their ability to simulate droughts, such as the persistence or inertia in the model states, such as soil moisture, recovery times for soil moisture given a certain meteorological input. And we don't necessarily look at those when we calibrate a model. We may just use a single integrated metric like a Klein-Gupta efficiency. So there's more to do to make sure that your model is a model that does simulate the right frequencies of response that are needed for drought. But this is all work. I feel like we have ideas about how to do it. We just need the projects that allow us to delve into them.
Thanks. There's another question from Bruce, and he's asking, are operational forecasters concerned for their jobs given these advances?
Yeah, I think there has always been that angle of discussion, in the moving particularly from in the loop to over the loop prediction, that it could require or lead to a loss of forecasting jobs. And I personally don't believe that's likely. I do think there could be a change in some of the jobs, but if you look at, for instance, numerical weather prediction, 30 years ago, there were people looking at surface analyses of observations and drawing, hand drawing fronts and things onto maps, and then developing warnings and alerts for the public. It was a very hands-on forecaster in the loop process. And now, for the most part, that over-the-loop transition has happened, and forecasters use NWP output, and they have sophisticated, tools and displays to analyze and manipulate NWP outlook, but they don't draw fronts on maps anymore, and we haven't had any loss of weather forecasters. I think that'll also happen in hydrology. We'll move slowly toward more over-the-loop approaches, and forecast office responsibilities will change a bit. The other thing is, all these earth science models, you look at the National Water Model, have not made a dent in the services provided by the traditional forecasting groups. And in fact, those are still going strong, getting more funding, building out their techniques. And so I think there's a real need, if earth science models are going to make a dent in operational forecasting that's actually used by management to make decisions, there needs to be more integration between those traditional groups and the earth science groups to understand why these earth science models are not making as much of a dent as they could be. You know, why is the quality not approaching what's being put out by traditional forecast groups? And hopefully that will happen.
Well, so will it be fair to assume that even though we are moving to hyper-resolution continuous modeling, a lot of this forecasting will be more as a complementary guidance for the local forecasters than as a competition to them?
Well, hopefully it will be, I would say they will be complementary, but hopefully they'll be, these two streams will dovetail so that these more process-oriented models will become the tools that are used and interpreted by the traditional forecasters. And eventually maybe these highly calibrated conceptual schemes will go away. I do think there's been a certain amount of arrogance on the part of the process-oriented model community to think that because of this complexity, they will, you know, almost automatically outperform and solve some of the problems the conceptual modeling community has not been able to. And what we've seen, I think, more generally is failure in that the high resolution or hyper resolution tools don't begin to approach the performance standards needed to be used for decision making. And so I think until, again, there is this integration and discussion between traditional forecasting communities with maybe simple models and the Earth system modeling community with the high resolution, the big computers, you know, we may still see this kind of repeated failure of these more complex schemes. And I'm not just talking about the National Water Modeling. Before that, we had HRAP, well, sort of HRAP-based 4-kilometer HLRDHM, which, you know, was a big initiative to go to distributed modeling. It didn't really replace the traditional forecasting. So we just need to be aware that both these communities know important aspects of the problem, and as long as they go in parallel, I think we won't be efficient in bringing them together and really harnessing what the two groups know for the betterment of both.
There's another question from Luis Arno, and probably it will be the last question for today. Do you think that we should focus on fine-tuning an operational forecasting system for certain applications, example, you know, like for droughts or versus floods, or should we aim to develop systems that can reliably predict all ranges of the spectrum?
Yeah, I think in general, I like the idea of developing a model representation of a watershed that fits into a system, you know, a forecasting system that really can do more than one thing. There may be limits on that. However, you know, for nowcasting, you probably do want a more highly spatially resolved system that can resolve all these little creeks and places that are engaged that lead to high impacts, you know, on human communities and society. But you may not want to use that same model for a 5-year ensemble prediction that informs a huge reservoir like, you know, Lake Powell or Lake Mead or Mica or, you know, one of the big dams up in Canada. I mean, you know, it might be nice if one model could serve all purposes, but just in terms of the computational efficiency and what you give up if you try to run a super fine resolved model at longer timescales, it's probably not your optimal solution. So I do think maybe the model basis and scale-aware models or scalable models, where you can take the same model and generate high resolution version and lower resolution versions and have similar performance. I mean, that may be the way to go to try to halfway have a seamless or integrated prediction approach.
Yeah, thanks. I previously said that was the last question, but there's one quick question that maybe we can quickly address. It's from Maureen, and the question is, has these models been used in over Africa, and what is the scale?
We haven't used the ZUMA model over Africa yet. I'm sure it will not be long. You know, Martin and his group have developed a North American implementation. It's only a small leap from there to take the same workflows and develop a global application. And I hope if that's possible, can collaborate in that effort. Certainly models like VIC sort of establish a pathway for doing that. And you see groups like Princeton running, you know, Pan-Africa implementations. But no, for Africa, I would look at the VIC modeling and potentially like GLOFAST modeling for MECMWF as well, and some of the other efforts like that.
Thanks. Thank you again, Andy. And I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. Just a note that next week we'll be having Dr. Chris Duxon from the Environment and Climate Change Canada, who will be providing a webinar entitled Snow Mass Remote Sensing, Current Capabilities and Future Opportunities. So please stay tuned. That will be all for today. Thank you again, and please stay safe. I wish you a good day.
Thanks, Praveen.